Good morning to one and all. Today we are going to take the second part of Module 1 of CET 203 Fluid Mechanics and Hydraulics for the students of APJ Abdul Kalam Technological University Civil Engineering students of second year. And we will be discussing today about pressure measurements. In the first part of module 1, we discussed about the basics of fluid mechanics and the basic terms involved in fluid mechanics. Today, we will be discussing about how pressure is measured inside a fluid. So, what exactly is fluid pressure? Fluid pressure is the force exerted per unit area by a fluid on a surface, and that is known as the fluid pressure, and pressure is given by the formula force exerted divided by the area of cross section. So notably the unit of pressure would be Newton per meter squared, or another common unit of pressure is Pascal, and the relationship between Pascal and Newton per meter squared, which is the SI unit, is that 1 Newton per meter squared is equal to 1 Pascal. That is, instead of using Newton per meter squared, pressure can also be expressed as simply Pascal, and it will still be the SI unit of fluid pressure. Now we come to the most important topic of measurement of fluid pressure, which is variation of pressure in a static fluid, or the hydrostatic law. Now, in hydrostatic law, it tells us how pressure is going to vary in a fluid as we move along the uh, depth of the fluid. That is, as we keep moving down the fluid, how pressure is going to vary in that fluid, and that is what we are going to discuss in this particular topic. So, hydrostatic law states that the rate of increase of pressure in the vertically downward direction must be equal to the specific weight of the fluid at that point. That is, um, this is actually giving us a relationship between rate of increase of pressure in the vertically downward direction and the specific weight, which we know is equal to density into G, or weight divided by volume. So anyway, just reading through the statement might not give you a good idea about hydrostatic law. That is okay. We will discuss this, and then we will come to the mathematical expression of hydrostatic law, from which you will understand this definition. So this is a cross section of a channel, and there are 2 points A and B over here. A and B are 2 points taken inside the fluid. Now, which do you think is greater? Pressure at the point A or pressure at the point B? Just by looking at it, you sense that pressure at point B might be greater than pressure at point A. Now, that is basically because there is more liquid above point B than that above point A. And so we understand that there is some relationship between the amount of fluid above a point and the pressure at the point. So hydrostatic law is basically helping us determine by how much pressure at B will be greater than pressure at A. So pressure is found to increase as we move down a static fluid. Static fluid means a fluid that is at rest. An expression that relates the relationship of pressure with the depth, that is, what is the relationship of this depth and the pressure at a point, that particular relationship is given by your hydrostatic law. So that is what we are going to be deriving soon. So consider a fluid element in a fluid at rest. So this is a fluid at rest, and I have taken a small fluid element here of depth dH and cross-sectional area equal to dA. Okay, I have taken a small cuboidal elemental area inside the static fluid with height dH and area of cross-section equal to dA. So let the cross-sectional area be dA, let the depth of the element be dH, let P be the intensity of pressure on the top face. Let the pressure at this face be equal to P. Now I'll single out this fluid element and draw the free body diagram of the fluid element over here. So this is the fluid element. This fluid element I have drawn it again over here. This is the depth dH of the fluid element. Now, considering all the forces that are going to be acting on the fluid element, the first force acting on the fluid element is the weight of the fluid element, which is given by dW, and it will be acting in the vertically downward direction. Now, another force that is going to be acting on the fluid element is the pressure force. Now, pressure force is force that acts due to pressure. We all know that pressure is equal to force divided by area. And so, pressure force will be equal to pressure into area based on the same formula. So, since small p is the pressure intensity on this top face, the pressure force acting on the top face is going to be pressure into dA. Why into dA? Because this is the area of the top face. The area of the top face is given as dA, and so the pressure force acting on the top face is given by P into dA. Now, similarly, a pressure force will also be acting on the bottom face. Now, the pressure force acting on the bottom face would be pressure acting on the bottom face into dA. Now, what is the pressure acting on the bottom face? I'll first show that to you. The pressure force acting on the bottom face of this element is P plus dou P by dou H into dH into dA. So again, you might be feeling confused as to how this term came about. Now, this pressure, the pressure acting on the top face is P. Now, dou P by dou H is the variation of pressure along the depth. That is the rate of change of pressure along the depth, let it be equal to dou P by dou H. It's like this. One pencil costs 10 rupees. So how much will 10 pencils cost? You naturally come up with the answer 100 rupees. Now how did you get that? Because with each pencil, it costs you 10 rupees more. Similarly, as you move down, the pressure keeps increasing at a rate of dou P by dou H. You have come down through a distance equal to dH. So the total increase in pressure is dou P by dou H into dH. So the total pressure over here would be P plus dou P by dou H into dH. And so the pressure force would be P plus dou P by dou H into dH into dA. Another common doubt that usually arises here is why is the direction of pressure in the upward direction at the bottom face and in the downward direction on the top face? This is because pressure always acts normal to the surface on which it is acting. That is, the surface area over here on the top face is pointing outwards, and so the pressure will point inwards. Okay, the area vector on the top face is pointing outwards, so the pressure will be pointing inwards. If you take the bottom face of this cuboid, the area vector is acting downwards, and so the pressure force will be acting upwards, opposite to the area vector. If you have studied area vector in mathematics, you would know. So this is how pressure force is going to act. Now, this element, so again, here I have explained that dou P by dou H is the rate of increase of pressure with depth, and dW is the weight of the fluid element. So I've just drawn the free body diagram. Now there are pressure forces acting on the side faces also. I'm not currently considering them because I'm going to consider the equilibrium of this fluid element in the y direction, that is in the vertical direction. Okay. So let's move ahead. This is the free body diagram of the fluid element. Now considering the equilibrium of the fluid element. Now why do I say that the fluid element is in equilibrium? Because the fluid is at rest. So the net force acting on the fluid element should be equal to 0. So in the y direction, I will get P plus dou P by dou H into dH into dA minus dW minus P into dA equal to 0. This is sigma Fy equal to 0. The net force in the y direction, I have equated it to be equal to 0. Now on solving, P into dA minus P into dA will get cancelled off, and I will get dou P by dou H into dH into dA minus dW is equal to 0. Now about dW. What is dW? dW is the weight of the small fluid element. Now how can you express the weight of the small fluid element? Weight is given by mass into gravity. So dW will be equal to dm into g, where dm is the mass of the fluid element. Now how do you express the mass of a particular quantity? Mass is given by volume into density. So the small dm can be written as dV into density. dV is the volume of the fluid element. Now, what is the volume of the fluid element? Volume of the fluid element is dA into dH. And so dW can be written as dA into dH into rho into G. So I'm going to substitute this particular expression for dW in the above equation. I will end up getting dou P by dou H into dH into dA is equal to dA into dH into rho into G. All the common terms can be cancelled off, and I will end up with dou P by dou H is equal to rho into G. Dou P by dou H, which was the rate of increase of pressure along the depth or variation of pressure along the depth, is given to be equal to rho G. What was rho G? You know that rho G is equal to specific weight small w. And so this is your hydrostatic law. Hydrostatics law stated that the variation of pressure in the vertically downward direction, which is dou P by dou H, is equal to the specific weight of the fluid, which is equal to rho G. So you have just proved hydrostatic law. Now this law is very important when it comes to measurement of pressure. So let's just take this case. There are 2 points A and B. A is at a depth of HA, B is at a depth of HB, and the distance between A and B is H. That is HB minus HA is given by H. Now let me take the hydrostatic law. Hydrostatic law states that dou P by dou H is equal to rho G. If I cross multiply, I'll get dou P is equal to rho G into dou H. So I can integrate this, and the limits of integration for pressure is from PA to PB, and for DH is from HA to HB. And I will end up getting PB minus PA is equal to rho G into HB minus HA. HB minus HA is nothing but H. So I can write this as PB equal to PA plus rho GH. That is, the pressure at B differs from the pressure of A by an amount equal to rho into G into H, where H is the distance between, or the depth difference between B and A. So PB is given by PA plus rho GH. This is a very important equation, and you will soon understand why. So let us consider the 4 points here. There are 4 points here, A, B, C and D. Let us consider how they are related. Okay, A is at a distance of HA, B is at a distance of HB, and the distance between these points is H. Now let's see what is the relationship between the pressures at these 4 points. What is the relationship between PA, PB, PC and PD? So if we take the relationship for hydrostatic law, we know that pressure increases as we move down in a fluid, definitely. So the pressures at B and D is going to be greater than the pressures at A and C. Hence, PB is given by PA plus rho GH. As we did in the previous slide, PB is given by PA plus rho GH. It differs by an amount equal to rho G times the distance between them. So PB is equal to PA plus rho GH, and PD similarly is equal to PC plus rho GH. But what is the relationship between PB and PD and PA and PC? PA is equal to PC, and why is it? Because A and C lie along the same horizontal point, along the same horizontal line, and when it lies along the same horizontal line, there is no depth difference between them. And when there is no depth difference between them, the pressures at the points A and at the point C will be equal. Similarly, pressure at B is going to be equal to pressure at D because of the same reason. They lie along the same horizontal line. So pressure at B and pressure at D are going to be equal. So these points lie along the same horizontal line, B and D, and A and C lie along the same horizontal line, and so PA becomes equal to PC and PB becomes equal to PD. Now we will look into the difference between atmospheric pressure, gauge pressure and vacuum pressure. The pressure exerted by the atmosphere on all things on the Earth's crust is known as atmospheric pressure. So as we are walking around, we feel that there is no pressure on us. But the actual thing is that the atmosphere is always exerting a particular amount of pressure on us, because of which all our bodily functions are regulated to that outside pressure. So it so happens that if the atmosphere decreases that pressure, it might create health problems. Okay, and so atmosphere is always exerting a particular pressure on all the things on the Earth's crust, and that pressure is known as atmospheric pressure. Now, the value of atmospheric pressure is 1 into 10 raised to 5 Newton per meter squared. Even though it is not visible, there is actually such a large amount of pressure acting on top of all of us. So, atmospheric pressure is given by 1 into 10 raised to 5 Newton per meter squared. Now, in pressure measurement, atmospheric pressure is usually taken as the datum. What do you mean by the datum? That is, the pressure measured at a point is described as this much Newton per meter squared above atmospheric pressure or this much Newton per meter squared below atmospheric pressure. That is, atmospheric pressure is taken to be the source or the datum above or below which pressure is usually measured. So, atmospheric pressure is considered to be 0 and the pressure is measured above or below the atmospheric pressure. Even though atmospheric pressure has a value equal to 1 into 10 raised to 5 Newton per meter squared, what we'll do is just like temperature, just like degree Celsius and Kelvin. Okay, 0 degree Celsius is taken as the datum and then temperature is measured either above 0 degree Celsius or below 0 degree Celsius. But actually, the actual measure of temperature is in Kelvin. Similarly, atmospheric pressure is taken to be 0 even though it is not, and pressure is measured above atmospheric pressure or below atmospheric pressure. So when pressure is measured above atmospheric pressure, that type of pressure is called gauge pressure. And when pressure is measured below atmospheric pressure, that type of pressure is known as vacuum pressure. So what you have to understand here is that if atmospheric pressure is taken to be 0, then gauge pressure would be a positive value. Gauge pressure would be a positive value, whereas vacuum pressure would be a negative value because vacuum pressure measures pressure below the atmospheric pressure. So this would be a small pictorial representation or a graphical representation, if you may, which shows the relationship between atmospheric pressure, gauge pressure, and vacuum pressure. So this is absolute zero pressure. Okay, this is absolute zero pressure, and this is your atmospheric pressure represented as P atmosphere. It is taken as equal to 1 into 10 raised to 5 Newton per meter squared. Now what we do is we take this value as 0 and then we measure above this value or below this value. So here you can see pressure A is measured above the atmospheric pressure, and pressure is greater than atmospheric pressure is measured above the atmospheric pressure, and so PA is known as gauge pressure. But the absolute pressure at this point is actually equal to P atmosphere plus PA. If you just express the pressure as PA, you are expressing gauge pressure. But if you are expressing the pressure as P atmosphere plus PA, you are expressing the actual absolute pressure at that point. Now, if we take another point, vacuum pressure PB. Here pressure is measured below the atmospheric pressure. That is, pressure is lesser than the atmospheric pressure and measured below the atmospheric pressure. So this is a negative value actually. Okay, because atmospheric pressure is taken to be 0 and pressure is measured below the atmospheric pressure. The absolute pressure of this point is going to be this, which would be P atmosphere minus PB, because this is the absolute zero pressure. So if we are measuring the absolute pressure at point B, it is going to be atmospheric pressure minus PB. Now, I'm just going to show you these 2 points A and B to make you aware of a particular point. What kind of pressure will be acting at point B and what kind of pressure will be acting at point A? You can see that this is the free surface. Always, whenever you have a free surface, the pressure acting on a free surface is going to be equal to atmospheric pressure. So here you have the free surface of water, and the free surface of water is going to be under atmospheric pressure. So in the given figure, what kind of pressure is going to be acting at the points A and B? Water surface is at atmospheric pressure. So point B, as you can see, is below the free surface, and so pressure is going to increase below the free surface. Right? Pressure increases as we move down in a fluid. So PB is going to be having more pressure than the pressure on the free surface. So PB is actually above atmospheric pressure. That is PB is having, or point B is having gauge pressure. When you're talking about point A, however, A is actually moving above or going up from the free surface, and so the pressure at A is going to be lesser than the pressure at the free surface. So the point A is going to be having vacuum pressure because we have been moving upwards from the free surface, which is having atmospheric pressure. Okay, so as we move down in a fluid, pressure will increase. As we move up in a fluid, pressure will decrease. You have to keep that in mind. So point B is the one that is having gauge pressure, and point A is the one that is having vacuum pressure. Let us do a problem. The pressure intensity at a point in a fluid is 3.924 Newton per centimeter squared. Find the corresponding height of the fluid when the fluid is A, water, and B, oil of specific gravity equal to 0.9. So if you are confident enough to do this problem, you can pause this video, move ahead and solve the problem and just check the answer for the solution. Okay. So otherwise, I'll just move ahead with the solution. So it is given that point A is at a depth h below. I have to find out the value of h. The pressure at A is given to me. Given that pressure at A is given by 3.924 Newton per centimeter squared, I have to find out at what depth it is below the free surface. Now 3.924 Newton per centimeter squared is actually not an SI unit. So we have to convert it into SI unit. And for that, Newton is an SI unit. So Newton can remain as it is. Centimeter squared has to be converted to meter squared. So 1 centimeter squared I am converting into 10 raised to minus 2 meter the whole squared. And so pressure at A is going to be 39,240 Newton per meter squared. Now PA is given by P atmosphere plus rho GH. If I want to calculate the pressure at A, it is going to be P atmosphere, which is the free surface, the pressure of the free surface, plus rho into G into H according to hydrostatic law. Now P atmosphere by convention is taken to be equal to 0, like I told you before. So we are going to measure the gauge pressure at point A. PA is equal to rho GH. And so now we have been given two cases. What happens if the point A is below water and what happens if it is under oil? So we'll take the first subdivision when the fluid is water. When the fluid is water, density is 1000 kilogram per meter cube. So PA is known to us, density is known to us, H can be calculated and H comes to 4 meter. This is what happens. That is, if the point A is at a depth of 4 meter below the free surface of water, the pressure at A is going to be 3.924 Newton per centimeter squared, and that is the question. Let's check the second subdivision. Second subdivision is asking you, what if the fluid is an oil of S equal to 0.9? Now when S is equal to 0.9, it is known that density is equal to 900. 900 kilogram per meter cube is the density. And so PA, which is given by rho GH, is equal to 900 into 9.81 into H, because the fluid is oil. So the pressure at A is given by 39,240 and Newton per meter squared, and so H can be found out to be 4.44 meters. So if the fluid was oil, for the point A to have a pressure of 3.924 Newton per centimeter squared, it should have been at a depth of 4.44 meter from the free surface. That is what this means. And so now I'll show you how pressure at A can be expressed in two different ways. Pressure at A can be said to be equivalent to 4 meters of water, because it has to be at a depth of 4 meter below free surface of water to have a pressure of 3.924 Newton per centimeter squared. Or pressure at A can be equivalent to 4.44 meters of oil of S is equal to 0.9. So this is another way of expressing pressure at A. So you can say that pressure at A is equal to 3.924 Newton per centimeter squared. Another way to express A is pressure at A is equivalent to 4 meters of water. So if it's given to you that it is 4 meters of water, you can convert and find out how much is it in Newton per meter squared. You just have to do rho into G into H, 1000 into 9.81 into 4. So you will get the pressure at A. If it is said that pressure at A is equivalent to 4.44 meters of oil of S equal to 0.9, you can do 900 into 9.81 into 4.44 to find out the pressure at A. So this is another way or another method of expressing pressure at a point. Instead of directly giving it in Newton per meter squared, you can express it as pressure is equivalent to this much amount of fluid. Okay. Now an open tank consists of water up to a depth of 2 meter and above it is oil of S equal to 0.9 for a depth of 1 meter. The figure has been given to you. Find the pressure intensity at subdivision A at the interface between the two liquids and subdivision B at the bottom of the tank. So you have to find out the pressure at this point and the pressure at this point. So you can either pause the video and try to solve this problem on your own and then just check the solution of how this problem has been done. Let me move towards the solution. So I've actually marked 2 points here, A at the interface and B at the bottom of the tank. Now at the interface, I know that PA is equal to P atmosphere plus rho oil into G into 1 meter, G into H, which is 1 meter. Okay. Atmospheric pressure is taken to be equal to 0. So PA would be equal to rho oil into G into H, which is 0.9 into 1900 kilogram per meter cube, which is the density of the oil, into 9.81 into 1. Or you will get pressure at A to be 8829 Newton per meter squared. If I am taking at the bottom of the tank, there are actually two fluids involved here, 1 meter column of water and 1 meter column of oil and 2 meter column of water. So at the bottom of the tank, the pressure intensity would be P atmosphere plus rho oil into GH plus rho water into GH dash. Another way of doing it is simply PB is equal to PA plus rho water into G into H dash. Simply because we have already found out PA. You can do that way also. So P atmosphere can be taken to be equal to 0. So PB is equal to rho oil into GH plus rho water into GH dash. Substituting, I will get 28,449 Newton per meter squared to be the pressure at B. Third question is, what are the gauge pressure and absolute pressure? This time absolute pressure is also being asked. At a point 3 meters below the free surface of a liquid having a density of 1530 kilogram per meter cube if the atmospheric pressure is equivalent to 750 mm of mercury, given that density of mercury is 13,600 kilogram per meter cube. So here the atmospheric pressure, like we had described earlier, instead of giving a Newton per meter squared measure for atmospheric pressure, they have given it to be equivalent to a fluid. So you know how to find out pressure when it is given to be equivalent to a fluid. Just do rho GH. Rho is whatever the density of that particular liquid is. Okay. So atmospheric pressure can be found out, and they have asked you what are the gauge pressure and absolute pressure at a point 3 meters below the free surface of a liquid having a density of 1530 kilogram per meter cube. So let's move on to the solution of the problem. So it's given that the point is 3 meters below the free surface. We know that PA is equal to P atmosphere plus rho GH. Okay. Now I want to measure or determine the gauge pressure at A. If I want to determine the gauge pressure at A, P atmosphere has to be taken to be equal to 0. So I'm going to take it to be equal to 0. So P gauge pressure is going to be 0 plus rho GH, where rho is equal to 1000 into 9.81 into 3, which is 45,027.9 Newton per meter squared. To determine the absolute pressure at A, I have to calculate the value of P atmosphere, which would be that P atmosphere cannot be taken to be equal to 0. It is given to be equivalent to 750 mm of mercury. That is, pressure at a point is 750 millimeter below the free surface in mercury. So rho mercury into G into H. So 13,600 into 9.81 into 0.75, which comes to 1,62 Newton per meter square. This is the actual value of P atmosphere. And so P absolute is going to be P atmosphere plus rho GH, where P atmosphere is not taken to be equal to 0. And so you will get 1,45,089.9 Newton per meter square. Next, we move towards an important topic, which is pressure measurement devices, or how to measure the what all devices are used to measure pressure. Now, there are two particular instruments that we are going to study. One is manometer and another is mechanical gauge. The figure on the right is going to show you this is a manometer and this is a mechanical gauge. Now, manometers read pressure in a fluid by balancing that fluid by a column of another fluid or the same fluid. That is, it balances the fluid in the right by a fluid on the left, by another fluid on the left. That is how it is going to read the pressure. In mechanical gauges, the pressure is going to be measured by balancing the column of fluid by a dead weight or a spring. That is, you are going to use mechanical means to measure the pressure of points in mechanical gauges. In manometers, you balance the column of the fluid by another fluid. So we will be discussing more detail about manometers in the coming slides. So manometers are of two types, simple manometer and differential manometer. Simple manometers are used to measure the pressure of the fluid at a point in a pipeline. So in a pipeline, fluid is flowing. You want to know the pressure at a point, you can use simple manometers. Differential manometers are used to measure the pressure difference between 2 points in a pipeline. So if you feel that there is a pressure difference in 2 points of a pipeline, you can connect a differential manometer not to find out the value of the pressure, but to find out the pressure difference between 2 points in a pipeline. Okay, so piezometer is the simplest type of manometer. It consists of an L-shaped glass tube connected to the point where fluid pressure has to be measured, where fluid pressure has to be determined. And so I'm going to connect this L-shaped piezometer to the cross section of the pipe. I want to measure the pressure at point A. Now the fluid from the pipe is going to flow into the piezometer and rise into the vertical limb of the piezometer. Let us say that the fluid rises up to a height equal to h. Now I know that pressure at A is going to be equal to pressure at B because they lie along the same horizontal line. Okay. So from the figure we can see that PA is equal to PB. That is, if I want to find out PA, it is enough that I find out PB. Now I know that I can see from the figure that PB is at a depth of h below the free surface of the fluid. And so PB is equal to P atmosphere. This is the free surface of the fluid. P atmosphere plus rho GH. Now by convention, P atmosphere can be taken to be equal to 0. And so PB I will obtain as simply rho GH. PB is equal to rho GH. If I get PB equal to rho GH, I can say that PA is also equal to rho GH because PA and PB, they lie along the same straight line. Okay, and so I have ultimately found out the pressure inside the pipe, that is PA, by using a piezometer. Now, the disadvantage of the piezometer is that higher the pressure at A, the greater will be the height through which the fluid is going to rise. So ultimately what will happen is, to balance the pressure at A, the fluid might have to rise up to 3 meters or 4 meters, which is going to make the piezometer a very bulky and impractical measurement device, because you cannot have equipments that are 3 meters or 4 meters high, which is almost as tall as a one-story building, just for measuring the pressure. And so the piezometer, in the case of measuring large pressures, becomes very bulky and impractical. So in order to overcome this disadvantage of a piezometer, we move ahead and go towards we opt for a U-tube manometer. Now this U-tube manometer is used to overcome the limitation of a piezometer. It consists of a U-tube shaped tube connected to the pipe. So instead of a direct L-shaped tube like a piezometer, it's a U-shaped tube, and inside this U-shaped portion of the tube, we are going to take a heavy fluid like mercury and place it inside. Now the reason why we place a very heavy fluid like density, the density of mercury is 13,600 kilogram per meter cube, which is 13.6 times heavier than water. Why we are placing such a heavy fluid like mercury inside the manometer is that if we place a heavy fluid like mercury inside the manometer, since its density is very high, to compensate or to measure very high pressure, it won't have to rise as much. Okay, it will only have to rise very little because its density is very high. To compensate for the pressure increase, every time pressure is increasing, a rho gh times the fluid should also rise. Because mercury is having very high density, the h through which mercury is going to rise is going to be very less because rho is very, very high. It has to rise only 13.6 times lesser than how much water has to rise. And so this will make the equipment like YouTube manometer a much more practical and less bulky equipment. The rise of mercury corresponding to the pressure in the pipe will be much smaller due to its high density. Thus, the equipment becomes much less bulky. So, I'm going to show you two cases where pressure at A is measured using a YouTube manometer. First one is when the pressure at A is gauge pressure. That is, pressure at A is having pressure that is greater than atmospheric pressure. Now, how can I say that for sure that pressure at A is greater than atmospheric pressure? Because the free surface of mercury is above the point A. That is, A is lying below the free surface. When A is lying below the free surface, it means that the pressure at A is greater than atmospheric pressure. Pressure increases as we move down. And so A is at a point below free surface. So A is having gauge pressure. So I am drawing two horizontal lines, one that is cutting through A and another at the free surface. So from here I can see that pressure at A is gauge pressure. I am taking another line XX at the interface between mercury and the fluid. Okay, so there is fluid inside this pipe and that fluid has flown up to here, and from here it is mercury. And so I am drawing a straight line XX at the interface between the fluid and mercury. I am going to take 2 points B and C on the line XX. Now since B and C fall along the same horizontal line, I can say that PB is equal to PC. Okay, and I have also measured the distances from B to A is H1 and from C to the free surface is H2. Okay, now how to determine the pressure at A? Now let's take the line XX. We know that since XX is a horizontal line and B and C are both points along XX, PB will be equal to PC. Now in the left limb, that is here, PB can be written as PA plus rho G H1. Okay, PB can be written as PA plus rho G H1 because it is a distance of H1 below A. PB is given as PA plus rho G H1. Now in the right limb at the same level, the pressure at C can be taken to be P atmosphere plus rho mercury into G into H2. Okay, PC is given by P atmosphere plus rho Hg. Rho Hg means rho mercury into G into H2 because that is the column of mercury above point C. Now I know that PB is equal to PC, so I can equate these pressures. So equating PB and PC, I will get PA plus rho G H1 is equal to P atmosphere plus rho Hg into G into H2. I know that P atmosphere has to be taken to be 0 by convention, and so PA plus rho G H1 is equal to rho mercury into G into H2, which means pressure at A is given by rho mercury into G into H2 minus rho into G into H1, where rho is the density of the fluid inside the pipe. Now, I don't want you to by heart this formula. What I actually want you to do is to understand how this problem has been done. The concept behind measuring pressure at A by a YouTube manometer. What I did was I took a horizontal line at the interface between the fluids and took 2 points in the left limb and the right limb, found out the pressures individually and equated them. This is the concept that is actually used in finding out the pressure using YouTube manometer. If you understand the concept right, you can do any problem on YouTube manometer. Now let's take the second case of pressure measurement in YouTube manometer, which is vacuum pressure. How do I know that pressure at A is having vacuum pressure? Because the free surface is below the point A. Point A is above the free surface. Free surface is having atmospheric pressure, and point A will then henceforth be having pressure lesser than atmospheric pressure since it is lying above the free surface. So I'm going to take two lines. Here I have taken line XX at the free surface. In the earlier case, I had taken XX at the interface. So whenever you have a manometer, take the line XX in such a way that it falls along the lower line. If free surface is lower, take XX along free surface. If interface is lower, take XX along the interface. So I've taken XX along the interface, XX along the free surface, and I have measured the distances H1 and H2, and I have taken 2 points B and C along the line XX, of whose pressures I know will be equal because they lie along the same horizontal line. Now, how to determine the vacuum pressure at A? Let us take the line XX. We know that PB is equal to PC. Now, from the figure, what can I say about PB? In the left limb, PB is given by PA plus rho GH1 plus rho mercury into G into H2. Okay, that is pressure at B in the left limb. Now pressure at C in the right limb will be equal to P atmosphere because it's the free surface, which will be equal to 0. Now I know that PB is equal to PC, so I can equate and I will get PA plus rho GH1 plus rho mercury into G into H2 is equal to 0, which means PA is equal to minus of rho mercury into G into H2 plus rho into G into H1. And hence we will get the value of pressure at A in the case of vacuum pressure also. We have only altered the position of the line XX to the free surface because free surface is lower than the interface, and we have followed the same concept, that is equating the pressures at points along line XX in the left limb and in the right limb of the manometer. Okay. So let's do a problem. Now always numerical problems on manometers are going to be like this. Figures will most probably not be given, and you will have to construct the figure of the manometer from the information that is given to you in the numerical problem. So you can go through the numerical problem and you can correspondingly find out or draw the figure from the details given to you. So here the right limb of a simple U-tube manometer containing mercury is open to the atmosphere, while the left limb is connected to a pipe in which a fluid of specific gravity 0.9 is flowing. The center of the pipe is 12 centimeters below the level of mercury in the right limb. Find the pressure of the fluid in the pipe if the difference in mercury levels in the two limbs is 20 centimeters. So we are going to use this data and we are going to construct our U-tube manometer from data. So we know that it's connected to a pipeline, okay, and they have said that the right limb, that is the first sentence, the right limb of the simple U-tube manometer containing mercury is open to the atmosphere, while the left limb is connected to a pipe. So we have drawn this much, okay. Now the center of the pipe is 12 centimeters. Okay, it is also given that the density is specific gravity is 0.9. So the fluid in the pipe A is having a density of 900 kilogram per meter cube. The center of the pipe is 12 centimeters below the level of mercury in the right limb. So this is the right limb and this is the center of the pipe. And so 12 centimeters below the free surface. This is the level of mercury in the right limb and the center of the pipe is 12 centimeters below the free surface in the right limb. Okay. Then it is also given that the difference in mercury levels in the two limbs is 20 centimeters. So if I take a line along the interface, the distance between the mercury levels in the left limb and the right limb is given as 20 centimeters. So this is the distances that I know. So this is obviously a case of gauge pressure. So I'm going to take the line XX at the interface and I am going to find out the pressure in the right limb at XX. That is over here. It's going to be P atmosphere plus rho mercury into G into 20 centimeter, which is 0.2 meter. So that is going to be the pressure at the right limb at XX. If I take the pressure on the left limb at XX, Okay, P atmosphere is taken to be 0, so pressure in the right limb at XX is going to be equal to rho mercury into G into 0.2. If I take the pressure in the left limb at XX, it is going to be PA plus rho liquid into G into 0.08. Okay, PA plus rho liquid into G into 0.08 will give you the pressure in the left limb, and these pressures in the left limb and the right limb at the level XX should be equal because they are along the same horizontal line. And so equating the pressures at XX, I will get rho mercury into G into 0.2 is equal to PA plus rho liquid into G into 0.08. Now I know the value of rho mercury 13,600. I know the value of the density of the liquid in the pipe A. S is equal to 0.9, so the density is 900. So I can equate and find out the pressure at A, and I will get it as equal to 25,976.88 Newton per meter squared. This is how you find out the pressure at A in a simple U-tube manometer. Let's take the second problem again. Here figure is not given. Simple U-tube manometer containing mercury is connected to a pipe in which a fluid of S equal to 0.8 is flowing at vacuum pressure. So it's directly given that it is case 2. That is, the fluid is flowing at vacuum pressure. The free surface of the mercury is going to be below the center line of the pipe. The other end of the manometer is open to the atmosphere. Find the vacuum pressure in the pipe if the difference of mercury level in the two limbs is 40 centimeter and the height of fluid in the left arm is 15 centimeter below the center of the pipe. So using these details, we can construct the manometer. If you want to do it on your own, you can pause the video, construct the manometer, and then check your answer. So we have a manometer and we know that it's having vacuum pressure, and that is why I have drawn the free surface of mercury below the center line of the pipe. Okay. Now according to the information given to us, the density of the fluid inside the pipe is S is equal to 0.8. So specific gravity is 0.8, which means density is 800 kilogram per meter cube. Okay. Then the center line of the pipe is marked by the horizontal line, and it said that the mercury level in the two limbs is, the difference of mercury level in the two limbs is 40 centimeter, and the height of fluid in the left arm, which is this, is 15 centimeter from the center of the pipe. So this is 15 centimeter. So this is 15 centimeter from the center of the pipe, height of the fluid below the center line of the pipe, and the difference in mercury in the two limbs is given to be 40 centimeter. So these are the details available to me. Now I can take, since in vacuum pressure, the free surface is taken to be the line XX, I can take this and I'm going to find out the pressure in the right limb at AA is atmospheric pressure, so it's equal to 0. In XX at the left limb, pressure is going to be PA plus rho liquid into G into 0.15 plus rho mercury into G into 0.4 over here. Okay, PA plus rho liquid into G into 0.15 plus rho mercury into G into 0.4. And these pressures have to be equal in the right limb and the left limb. So when I equate it, I'll get 0 equal to this term. And on solving, I know everything in this equation except for PA. Everything else is known to me. And so when I solve it, I will get the pressure at A to be equal to negative 54,543.6 Newton per meter squared. And I hope that this is now become simple to you. So we have studied about differential manometer. We will be now studying, we studied about simple manometer. We will now be studying about differential manometer. So you can see that this U-tube manometer over here is connected to two pipes. Okay, so this is a simple differential manometer and this is an inverted differential manometer. It's connected in an ulta fashion. It's connected in the upside down fashion. Okay, and differential manometers, instead of measuring pressures, absolute pressures at points, they measure the pressure difference between two pipes. Okay, how it is done? We'll take a look into it. So devices used for measuring the difference of pressure between 2 points in a pipe are known as differential manometers. And here we have case 1. You can see that the pipes are at different levels. And here you can see that the pipes are at the same level. So we can usually take it to mean that here it is used to measure the pressure difference between two different pipes. And that is why there are two different levels. When the pipes are at the same level, then this equipment is used to measure the pressure difference between 2 points in the same pipe. When it's in the same pipe, the pipes are at the same level. Here pipes are at different levels because they belong to two different points in two different pipes. Okay. So we'll straight away start with a problem, because the concept involved in differential manometers is same as the concept involved in simple manometers. So a pipe contains oil of S equal to 0.9. A differential manometer connected to 2 points in the pipe shows a difference of mercury level equal to 15 centimeter. Find the pressure difference between the 2 points. Okay, this is a simple question. Pipe is containing oil of S equal to 0.9 and a differential manometer is connected to 2 points in the same pipe, which means that the two pipes are at the same level. Okay, the differential manometer is connected at the same level to two different points, and the difference in mercury level is 15 centimeters. Find the pressure difference between the 2 points. So let us construct the figure. Since it's given that A and B are points in the same pipe, they're at the same level. Okay, they're at the same level, and it's given that the difference in mercury level is 15 centimeters. But I don't know this depth. I don't know the depth below up to the interface. What is the depth below A? So I have just simply written it as H. Okay. So now the working of this problem is very similar to that of your earlier simple YouTube manometer problems. We just equate the pressure in the right limb and the pressure in the left limb at XX. I am taking 2 points C and D along XX. From the figure I know that PC is equal to PD. Now in the right limb, the pressure is PB plus rho into G into H plus 0.15. This is the total distance. In the left limb, similarly, I'll be having PA plus rho into G into H plus rho mercury into G into 0.15. Okay. Now these two pressures are equal. So when I equate it, I'll get PB plus rho G into H plus 0.15 is equal to PA plus rho GH plus rho mercury into G into 0.15. Now it's given that density is 0.9. So rho is equal to 900 and rho mercury is 13,600. PB and PA you can bring it to one side, and all the other terms you can take it to the other side. So I'll get PB minus PA is equal to rho mercury into G into 0.15 minus rho into G into 0.15, or I will get the value of PB minus PA to be equal to 18,688.05. So you can see here that the concept involved in determining the value or the answer is the same as that of a simple YouTube manometer. You just take the line XX along the interface, along the lower interface here, whichever is in the earlier one you had taken the lower value. If it's a simple YouTube manometer, XX was taken at the interface if interface was lower than the free surface, and free surface if free surface was below the interface. Here there are two interfaces, there is no free surface. So whichever is the lower interface, we will take XX at the lower interface, that's all. Okay. And this is how you do the problem, and what you have actually found out is the pressure difference between B and A. You have not found out the values of pressure at either point, you just found out the pressure difference, and that is the question also. The question also was asking you just to find out the pressure difference between B and A. Here we are lucky because here the figure is given to us. A differential manometer is connected at 2 points A and B of two pipes. There are two different pipes as shown in the figure. Pipe A consists of a liquid of S equal to 1.5. So here it's having a density of 1500 kilogram per meter cube. And pipe B consists of a liquid of S equal to 0.9. So here density of the liquid is 900 kilogram per meter cube. The pressure at A and B are given to be 1 kilogram force per centimeter squared and 1.8 kilogram force per centimeter squared. So surprise, PA and PB are also given to us. We have to find out the difference in mercury level in the two limbs of the manometer. That is, this distance is what you are supposed to find out. Now, one very striking thing that comes to me even before I start the problem is kilogram force per centimeter squared. This is not SI unit. Whenever you're doing a problem, you have to convert the value into SI units. So 1 kilogram force is equal to 9.81 Newton and 1 centimeter is equal to 10 raised to minus 2 meter. So using that, we have to convert the kilogram force per centimeter squared into Newton per meter squared before even beginning with the problem. So we'll go into the solution of this problem. So this is the figure I've taken XX at the lower interface and I've marked the difference in mercury levels as H. Now PA is given by 1 kilogram force per centimeter squared. This is 1 into 9.81 Newton divided by 10 raised to minus 2 meter the whole square. Centimeters 10 raised to minus 2 meter. Kilogram force is 9.81 Newton. Or I will get 98,100 Newton per meter squared as pressure at A. Similarly, pressure at B, 1.8 kilogram force per centimeter squared. I will get it as 1,76,580 Newton per meter squared. Okay, so I've converted PA and PB into SI units. That is most important thing. Now after that, the pressure at XX in the right limb, PB is given in the right limb. Pressure at XX is given by PB plus rho B. Here density of the fluid is different from the density at A. Here it is 900, here it is 1500. So rho B is 900 and the distance from the center line of B to the line XX is H plus 2. So PB plus rho B into G into 2 plus H. In the left limb, it is given by PA plus rho A into G into 5 plus rho mercury into G into H. So now at the left limb and the right limb at the level XX, the pressures are equal because they are along the same straight horizontal line. Equating the pressures, we will get an equation like this. Values of PB and PA are known, rho B and rho A are known. The only value unknown here is H. And when you solve for it, we will get H is equal to 0.1811 meter or 18.11 centimeter. Now we are moving on into another topic, which is inverted differential manometer. So in the discussion of differential manometer, we had actually shown a picture of this figure. Inverted differential manometer is when a YouTube manometer is connected in an inverted fashion, upside down. This is usually done when the pressures of the fluids flowing in A and B or two pipes are low. That is, we are having to find out the difference between two low pressures. Now, when the pressure is low, we usually don't resort to simple YouTube manometers like mercury, because usually if it is in vacuum pressure, the fluid will try to suck in the mercury because mercury is so heavy. And if the pressure in the pipe is below atmospheric pressure, mercury will get sucked into the pipe, and we don't want that happening. Okay, and so in order to measure low pressure differences, we will usually resort to inverted YouTube manometer. Like simple YouTube manometer, instead of mercury, there will be another liquid of density rho L, which is lighter than the liquid inside the pipe. Will be there inside the inverted YouTube manometer. Okay, so now let's move ahead. Let's do a problem. The figure is given to us. Water is flowing through two different pipes to which an inverted differential manometer having oil of S equal to 0.8 is connected. Okay, so the density of the manometric liquid is 800. The pressure in pipe A is given by 19,620 Newton per meter squared. Find the pressure in pipe B. All the distances are given to us. Now, where to take the line XX? XX, in the case of inverted differential manometer, is taken on the upper interface. There are two interfaces here and here. XX is usually taken on the upper interface, and that is the only difference in the case of inverted differential manometer. So let's see how this problem is done. So this is the diagram of the inverted differential manometer. This is the line XX. Okay, I've taken the XX at the upper interface, and manometer liquid has S is equal to 0.8, so the density here is 800 kilogram per meter cube. So now the pressure at xx. Okay, we are going to find out in the right limb and the left limb. If I take the right limb, okay, it is going to be, now you can see here that we are actually climbing up from the center line. Unlike the previous cases where we were moving down from the center line, here we are moving up. And so the pressure at xx in the right limb is going to be PB minus rho into G into 0.1 minus rho liquid into G into 0.12. Actually, pressure is decreasing because as we move down, pressure increases. As we move up, pressure decreases. So in this case, the pressure is decreasing from the center line. So the pressure at xx in the right limb is PB minus rho into G into 0.1 minus rho liquid into G into 0.12. And in the left limb, if you take, it would be PA minus rho A into G into 0.3. Okay. So this is the pressure in the left limb and the right limb. You can see the difference that it is actually reducing. Now these pressures are equal, so we can equate them. Now we know the pressure at A and we are asked to find out the pressure at B. And the densities are known to us. So we will get, when you substitute, that pressure at B is equal to 18,599.76 Newton per meter squared. And this is the manner in which we calculate we do problems on inverted differential manometers. Let's do one more problem on inverted differential manometers. The inverted differential manometer is connected to 2 points A and B, both of which convey water. Manometer contains a fluid of S is equal to 0.8, so this is density is 800 kilogram per meter cube. For the given manometer reading, find the pressure difference between A and B. It's a simple, straightforward question. The dimensions are given. You just have to find out the pressure difference between A and B. Where will you take the XX line? XX line should be taken wherever the upper interface is coming between the liquid and the manometric liquid. So we will take XX over here. So this is the figure. I'm going to take XX over here. Now let's check if all the distances are known to us. The distance from AA to XX is known. The distance from B to A is known. And the distance from B to this upper interface is known. This distance, however, is not known. We also require this distance from the lower interface up to the line XX. And so we know that this total distance is 50 and that this distance from B to the lower interface is 30. And so we will be having this distance as equal to simply 20 centimeter. Okay. So this is the value 20 centimeter, that unknown value which we have simply calculated. Now we are going to find out the pressure difference between A and B. The pressure at XX in the right limb, that is over here, will be PB minus rho water into G into 0.3 minus rho liquid into G into 0.2. The pressure at XX in the left limb is going to be PA minus rho water into G into 0.3. And when we equate the pressures, we will get this value. Density of water is known, density of the liquid is given to us as 800 kilogram per meter cube. And so we will find out PB minus PA to be equal to 1569.6 Newton per meter squared. So basically this whole lecture was to explain pressure measurement devices and how pressure is measured. You can see that we have explained manometers in detail, and all the problems in manometers are explained on the basis of hydrostatic law. So the derivation of hydrostatic law and the result of hydrostatic law is also important, an important takeaway from this lecture. So I hope that this lecture is clear and it has been a fruitful lecture to all of you, and that you have understood